Hello and welcome to HPC. In this series of videos, we will be introducing you to the concepts of parallel computing. But then before we start talking about parallel computing, we first have to look at something called serial computing, look at how it has or it started and then where it has gotten to its limits and then the reason or the purpose of or the importance of parallel computing in our lives. These would help us to appreciate the efforts or the things needed in order to compute in parallel. So without wasting much time, let's get started. I'm Joseph Sedem, a tutor at HPC. We are glad you are learning parallel computing with us. Okay, so by the end of this lecture, this particular one, we would have a feel about how earlier computers work, and then look at the change in the CPU architecture as well as that of the memory architecture, and also look at what serial computing is all about. Before we start, we first have to make some assumptions, right? For the purposes of better understanding, we would have to assume that one core or one CPU core, which is equivalent to one CPU, the central processing units in the past, only performs one process at a time. So later you get to know what a process is, but then let's keep in mind and know that let's assume that one CPU core just does one processing or one process at a time, and then we also have to assume that the next process only starts after the previous process has been completed. So it means that two processes cannot start at the same time. Let's make that assumption. And then we also have to assume or know that when I refer to CPU or when I call CPU or mention the name CPU, I'm referring to the physical hardware that is placed in the system unit or on the motherboard. But when I call the word processor or I mention the word core, I'm referring to the compute cores, the things that actually perform the processing or executes the task. So if we have all these assumptions right, we can follow well and then probably understand what is going to happen or go on in the next lecture. Okay, so first, what is serial computing? So basically it's a type of computing in which one task is executed and completed at a time, right? A single task is executed. While it's executed, it is also completed at a time. So the tasks are completed one after the other, and then all the tasks are executed by just a single processor or a processor in series, which means that all the tasks, if you have 10 tasks, they get completed one after the other. Now, we should bear in mind that these tasks are handled by a single processor, right? These tasks are handled by a single processor, which yields poor or low performance. So if these tasks or 10 tasks or 20 tasks are supposed to be handled by a single processor, obviously the performance or the time which it would take to finish processing or running that task would be poor if the workload on the processor is enormous or is quite large, right? So if you're supposed to finish running like 100 processes or 1000 processes, it's going to take a longer time since it's just one processor processing the task one after the other. So basically that's what serial computing is about. You running a task one after the other, and then the next task can only run while the first task or the initial task has been completed. Okay, but then let's look at how the computers or evolved or originated. So the earlier computers, right, were designed, that's the digital computers, right, were designed based on the von Neumann architecture. So the von Neumann architecture is basically says that the computer has an input and output device, right? Input to input data, output to display the process data or information on the screen or anything, and then it has a processor, that's a central processing unit, the CPU that will process the data that it takes from the input, and a RAM or a memory. Sorry. So this memory could be the one that stores information permanently or the one that stores the information temporarily. That's the RAM, right? So it has memory to store information permanently or temporarily, and then a processor to process the information, as well as input and output devices, right? So basically, earlier computers, that's the digital computers, this was the architecture or the basic architecture they had, right? Now let's look at the application processing cycle. So if we have an application, say we have an app, right? This app is supposed to compute the area of a triangle. Bear in mind, the task is to compute area. So area of a triangle, right? And then this app, or this is the app that's supposed to be executed. Before this task or this app gets executed, first it has to go into the memory, right? We need to pull the app or the instruction or the set of instruction will be uploaded first into memory, that's the RAM, and then the set of instructions will then be called by the processor, the CPU, before it gets executed or it gets processed. While at it, the set of information that the processor needs frequently to keep using frequently are stored in the cache memory of the processor. So the processor also has a cache memory where it stores relevant information that it needs to be getting or it needs to be using frequently. So first, you launch your application. Let's say you double click on your application, the area app. This app or this application gets uploaded or loaded into the memory, that's a RAM, right? And then after it's being loaded into memory, the processor comes for the set of instructions one after the other and then executes them. The sets or the parts that it has to be visiting frequently are stored temporarily in the cache memory of the processor. Basically, that's how running of application or processes go happen in the system unit, basically. Okay, now we've been hearing the word process. So what is a process? A process is basically an instance of an executing program. So which means that if you double click on an app, if it's Beacon, Google Chrome, if you double click on it and your mouse starts, your cursor starts showing the processing sign, it means that you have initiated a process, you started a process. Basically, that's a process. So any executing or running program. But then we should know that every process has its own space in memory. Bear in mind, I say that for the processor to start or run or execute any process, any task, it has to first store the task in memory, right? So if this task is being stored in memory, then it down goes from the memory and then start being executed by the processor. Keep that in mind. So basically, that's what a process is. And then threads, right? We will be hearing about threads later down the line. So let's talk about what threads are. So basically, a thread is just a compute pathway to engage more processing cores, right? So this is trying to say that it's a path that you can use to ask for help in processing some application or a task. So basically, we can say that a thread is just a sub process or a lightweight process. So threads are basically sub processes or lightweight processes. So we can look at threads as, let's say, if you have a process of executing a huge task, and then this task also has subtasks under it. Instead of these tasks to wait until the main task gets executed, it then generates other paths, right? Bear in mind that these paths are still in the memory, right? But then these paths are just to help take or help get help get help from the other cores in the system unit. But basically, just think of a thread as a sub process for now. Now know that a process can contain one or more threads, right? If you have sub-processes, it means that in just one big process, you could have multiple sub-threads. So for instance, if you launch the Google Chrome browser, right, you could open that browser, right, which is the main process, and then inside the browser, you could open a new tab. So if you open a new tab in the browser, instead of being another process, it then creates a thread or uses a thread to open that tab. So this tab is also part of the process. You could also decide to be downloading movies or music or any other thing. The downloader, that's the inbuilt Google downloader, Chrome downloader, would also be a new thread, which is also part of the main Google Chrome process. Basically, that's it. And then since a process can contain more than one thread, it means that what multiple threads, right? Multiple threads share the same space in memory as the process. So it means that if you have one process and this process has a space or has occupied a space in memory, and this process has generated like 10 threads, you've opened the browser, you open like 10 tabs, and then you are downloading movie, doing other things, same in the browser. These processes are occupying the same space. Threads don't create their own space in memory. They don't go and create their own space, but instead they share the same space as the process. So basically keep that in mind for threads. Going forward, we would use the threads and then you would see what they mean. Okay, now, so in serial computing, we said that a process or a task gets processed one after the other, right? Which means that should you have a lot of tasks, the CPU or the processor gets overwhelmed, right? And as it gets overwhelmed, it takes a longer time for the processor or the computer or the CPU to finish processing the task or the application or finish running the application. So the earlier days, they sought to create a lot of things that would help improve the speed, the compute speed of the machine or the computer. And the first thing, not the first, but then one of the things they sought to do was to increase the clock speed. And the clock speed basically is the processing speed or the operating speed of the processor, right? And then clock speeds are measured in cycles per second. So if we have, let's say, time here, right, and time is measured in seconds, and this is our frequency, right, then a cycle will probably, so this will be 1 cycle, 2 cycles, 3 cycles, 4 cycles. So basically this would be what, 4 hertz. 4 hertz per second, right? So basically this is this is 4 hertz, that's cycles per second. So not 4 hertz per second, but 4 hertz. So we could have processing speeds to that can go like, let's say 2.5 gigahertz, right? And then megahertz and the others, which means that we have giga is 10 exponent 9, so which means that we would have lots of cycles per second. But then increasing this clock speed, the clock speed was back in the days in megahertz, but now they've been able to push it to gigahertz. But then the limit or the limitation for increasing clock speed is that the more clock speed or the higher the clock speed, the more heat that gets generated, which means that you should worry more about cooling of the CPU, right? So which means that they could barely push or increase the clock speed, or the clock speed can barely move or can barely be pushed, which means that we have to look for or sort other alternatives if we have to increase the task or the capability of the processor. So the next thing that came in mind or that they had to do was vectorization, right? So the concept of vectorization is basically the process of converting an algorithm from operating on a single value at a time to a set of values. So it means that, let's say, if you have a processor or you have a task that is supposed to add elements, let's say add this element or these numbers together, right? Ideally, it will take 1 and then do 1 plus 2, that will be 3, and then 3 plus 3, that will be 6, and then 6 plus 4, that will be 10, right? Now, looking at the time it will take to compute each task one after the other, right? This takes time. So the concept of vectorization comes in the sense that instead of running this one after the other, they then decide that no, let's take these elements as vectors, right? And this is called vector units, right? Vector units. And then this vector unit, so it takes 1, 2, 3, 4. So you can have, let's say, 256 bits, right? Bits wide of this vector, and then this would take 4 of a 64 bits double precision, 64 bits double precision doubles or integers. So basically, if you have this, right, it's going to take 4 of this. So let's say these are 4, and the total size of this is 256 bits, right? And then you have to run the summation on these things. Instead of it's running 1 plus 2 plus, after 1 plus 2, and then 3 plus 3, and then 6 plus 4, it then takes all these elements and then adds them at the same time, or adds them together to give us 10 straight up, instead of doing them one after the other like the loop form. So basically, you see that this approach, if it takes a minute to compute 1 plus 2, so it means that basically it's going to take like 1, 2, 3 minutes to compute this. But in this situation, it just takes 1 minute to add all these things together. So the concept of vectorization also helped in increasing the speed, or the processing speed, or the computation speed, right? Another thing that they introduced, or that was done in order to increase the computational speed of serial computing or serial processing, was the multithreading. Now, the multithreading is basically a process, is basically where a process, right, is being divided, or is divided into multiple threads. So as we said, you have, let's say, the Google Chrome, right? Now this Google Chrome, once you double click on the Chrome browser, it becomes the process, right? A process that has been initialized. But then inside this Chrome, you want to open a new tab, or let's say you want to browse or open a new tab. Now, instead of this new tab also starting all over again as a new process, or instead of you opening a different section or a different version of a different instance of the Google Chrome to browse this thing, Google allows you, or the Chrome browser allows you to open a new tab inside the same Chrome process, right? And you could open several tabs inside the same Chrome process. Now, basically, what is letting us do this, or letting your computer process this at the same time, is a multi-threading. So which means that the computational path that is being used to process this tab is different from this one, and is different from this one, but they are all in the same process, right? Which means they are all occupying the same space in memory, but then are being executed separately. That's how come you can be searching something here. When you run, you can open to a new tab, look for another thing, open a new tab, look for another thing. When you come back here, you see that this search will be completed, this search will also be completed, and then this search will also be completed. You could also start downloading. While you are downloading, you continue to browse other stuffs. This is happening, or this is made possible because of the concepts of multi-threading. So multi-threading does this for us, right? But then later, Intel also decided to introduce the concepts of hyper-threading, right? So hyper-threading in this sense is just like multi-threading, but this time around, hyper-threading changes or divides physical CPU, right, into virtual CPUs, which means that it makes, let's say, one CPU, physical CPU, that's the hardware, look like two or more virtual CPUs. So the system thinks that you have more than one CPU. Bear in mind that this is quite different from a CPU having multiple cores, right? This, you have just one CPU, but then even though you have one CPU, the system can think, or the system will be made to think that what, you have multiple CPUs, which means that if this CPU can have multiple threads, this virtual CPU, so if you have, let's say, a CPU that could have maybe 10 threads, the virtual CPUs would have 10 threads each, which means that in total you could have 20 threads. So each virtual CPUs could also have its own multi-threading done. So this virtual CPU can best be illustrated if you try installing a virtual machine. So let's say you have a Linux operating system as your base, and then you try installing Windows on it through a virtual machine, or vice versa, you have Windows as a base and you try installing Linux as a virtual machine. The Linux in the VM or the virtual machine will still have the same processor you have, Core i7, 10th gen, a lot of specs, the speed and everything will still be there, while your Windows is still processing. Bear in mind that the Windows is the one that you use to launch the virtual machine, right? But then this Windows is still see its own CPU, while the Linux is also seeing its own CPU when you get to the properties there. So basically that's the concept of hyperthreading, and this hyperthreading can make us do lots of stuff fast. Because imagine you open Google Chrome or browser or any other app on your Windows, and then you open your VM and you are still browsing or doing your programming and other things inside the VM. You see that the hyperthreading helps compute tasks faster. Now, while the architecture, the CPU architecture keeps changing, let's not forget that the memory or the computer memory holds the information temporarily for the CPU. So which means that the speed or the processing speed of a machine does not only depend on the processor, but then also depends on memory, how fast the data is being transferred from the memory to the CPU and forth. So it means that the CPU, the memory architecture had to also change, and it did change throughout the years. So first they moved from DDR1 to DDR2, which improved the speed that was in DDR1, and then DDR3 also did same, and currently DDR4. So it means that they keep increasing the transfer rate or the speed, the transfer of data between the RAM and then the processor. So basically that's the view of the RAM architecture. But then after all these things are being done or have been done, still the computational tasks keep increasing. We still have data in large quantities, which means that just using a serial code or serial programs or executing code serially or performing serial computing is just not enough, right? Because we still have this single CPU. Bear in mind the single core, yes, now it has vectorization, so it processes stacks simultaneously. It has multi-threading, it has been multi-threaded, and then probably has some virtual CPUs as well. But then the computational tasks keep getting higher and higher, and then we would like to increase the speed at which some programs or some tasks gets executed, right? So because we still want more speed and more accuracy, and we want to save more time, the concept of parallel computing had been introduced, where we try and see whether instead of running one program at a time, we can actually execute 10 programs or multiple programs, and they will all run faster at the same time. So instead of opening one Google Chrome browser, and then after we finish browsing, yes, probably with multiple tabs, and then when we are done, we have to close the browser and then open a different thing. Instead of doing that, we want to be able to open the Chrome browser and multiple tabs at the same time. So that's basically the concept of parallel computing. And then we would be seeing that in the next video. So in the next video, we'll be looking at parallel computing with uniprocessors, how the notion of parallel computing was initiated with uniprocessors. And I'll see you in the next video. Thank you.